Okay, welcome to the tutorial for Catia V5 release 20. Here we are going to create a crank rocker giving 45-degree rocker rotation with equal interval time forward and backward. Okay, let's open Catia. Then from start mechanical design, take SketchUp. Then give the name here and click OK. Then click on any plane from here or from the directly from the tree. Okay, then take line tool from the then estimate a rocker length as your convenience. So here I took it as 100 millimeters. Okay, then I clicked that and I clicked on the initial position and created the line. So ensure that the line is already constrained. When the dimension is not on in between two green lines, green arrows, it means that the component in the sketcher is constrained. Then click on the line and again create another line of the same dimension. Here it is 100 mm. The initial positions of both these lines are the same, so the second line is also constrained. Next thing is we want to fix the constrained angle between the two lines, and this angle is called as theta. So theta is the angle of rotation of the rocker. Then take the constraint tool from the toolbar and click on both lines, and angle constraint rotation will come. Click, then double click on the angle constraint notation, then redefine the value to the theta value, that means here 45 degree, then click OK. So the angle is constrained, and wherever we make a rotation, the whole system is constrained and the system undergo a complete rotation. Okay, then whenever the forward and backward time ratio is same, the connecting rod and crank will align in a same line at the maximum rocker position and the minimum rocker position. So just take another line, then click on the second end of the second line, then just draw it larger and ensure that the line coincides with the second point of the first line. Okay. Then connect the initial position of the two rocker positions and the finally defined lines end. Okay. Now we have the rocker length as 100 here, and we have the fixed distance between them as this line, that's 189.277. Okay, then we have this line. Note the length of the fix. Then we have this line, the dimension of this line as 203.466. Okay, then note it, and from the toolbar click here and take the eraser tool, quick trim tool, and trim this thing. So measure the length of the remaining portion of the line, that is 76.537. and we know that half of this section of line is a crank distance, that is 76.537 by 2 is the crank distance. Then the earlier measured line, which was drawn as a third line, is a combination of the length of connecting rod plus the crank. So my subtracting the length of the connecting rod from the length of the crank from the third defined lines will give the length of the connecting rod. Okay, so we have got the length or dimensions for the 4 bars in the mechanisms as per our input. So we can just close this sketch base. Now we have got the dimensions of the 4-bar mechanism as the connecting rod length as 38.2685 mm. Then the crank length is 38.2685 mm. Connecting rod length is 165.1915 mm. Then the rocker length is default one, and it is 100 millimeters, and the distance between the first and third link, that means the length of our fourth link, is found to be 189.277 millimeters. So we can go to the parts workbench to create the links. So click on start, mechanical design and part design, then type it as crank. So we are going to create the link as crank. So then select a plane to sketch. So when we create a mechanism, it's more convenient if we are selecting the same plane in each stage of in every stage of creating links for sketches for different links. So click on, so I am taking here the YZ plane, so I'll click on the YZ plane and select sketch from here. So we want to sketch a link. So as per my suggestion, the better sketch for link is elongated hole. So we can click on the arrow here, the near to the rectangle, then select the longer hole, then click on the 0 0 position, that's initial position, absolute position, then select in the sketch tools toolbar, enter your crank. We are going to create the crank link here. Enter the crank length, that is found to be 38.2685, then click enter. So we can now position the line, so make it horizontal, or you can enter the angle here, that means 0 or 360, then we have created it. Okay, then conveniently fix the width of the link. So I think it's better to select it as 5 millimeter radius. So the sketch is created. So now we can exit from the sketch workbench. Then it's now in the part workbench. So click on pad, and here also take a convenient width for the link, and I select it as 10 millimeters here. Okay, then it's created. So we want to color it, we want to color the each and every separate links separately. So I'm taking the color for this link as red. So I right click on the part body in the tree, then properties, then graphic, then this here there's a fill color option, so I select the color as red and applied it. Okay, then I want to save this part, so I click on file, save. Then I have to create a separate folder. When in Catia, whenever you are going to create a kinematics or an assembly, it's better to place all your part files in parts files and assembly files. That means almost all the root files in the same folder. So I renamed it as 4-bar mechanism folder. Then I saved the part as crank here. Okay. Then I want to create another part, so from mechanical design, part design, the next part is our connecting rod. So the connecting rod is to create. So remember that we have to select the same plane in every part. So the same plane, that means the YZ plane. Then I click on the sketch workbench, so elongated hole tool, then click on the initial position. Then I want to enter the length of the connecting rod, and that's found to be 165 point 1915. Then I made it into horizontal position. Then I have to define the same radius here, that's 5mm radius. Then exit the workbench, then click on pad tool, then enter the pad length, that means the width of the link, and right click on the part body, properties and graphics, and I have to color it as yellow, and apply, then file, save. Saving the same in the same location, the connecting rod is already saved. Then close and file, mechanical design, part design. Here I want to create the rocker, so type it as rocker. Then click on the YZ plane, sketch, elongated hole tool, click on the absolute 0 position and enter the length of the rocker, and it is default and it's 100mm. Then define its radius, that's 5mm. Then exit the workbench, then click on pad. Then the pad length is 10mm again, and click on the part body, properties, then graphic, and I have to color it as a green. Okay, then click OK, then file, save. Save in the same location. Then our last part, fourth and last part is I call it as the fourth link or a fix. So this is a workbench for a fix. Select the YZ plane, sketch, then elongated hole, then click at the initial position, then enter the length of the fix, that means 189.277. Okay, then I click enter, then define the radius, that's 5mm. Then exit the workbench, click on pad, then enter the pad length, that's 10mm. Then right click properties, graphic, fill color, it's black. Black is better for a fixed link. So we are going to save the same fourth link in the same folder, so click save, then close it. So we want to join all 4 links into one platform, and there is a third platform for Catia. We came from the sketch, there's the first platform, then to the part platform, and now it's our assembly platform. So click on start, start is where our every work starts, then mechanical design, then assembly design. So click on the applications in the tree and click existing components, then locate your folder, that is 4-bar mechanism, and select all the components and open. And it will take a few seconds to load all the components. Yeah, our four links are here, so all of them are joined because all the four links are made in absolute position. So just explode it from the manipulation toolbar, then apply it so it's exploded. So all the four links are in the same platform, then we want to join them and we want to make a revolution. So click start, then from digital mockup to DMU kinematics. So it's now in the DMU kinematics platform. So we want to create the joint. So in every mechanism we have to fix at least one position. That's a minimum criteria for every motion or kinematics, especially in kinematics. So we want to fix. That's the better thing to be fixed is the fix part itself. So click on fix in the tree, then click on this anchor signed tool, that's fix part. So click on it. So if you want to fix, you should have create a new mechanism. So a dialog box will automatically come. So from here click new mechanism and just name it as the default, that's mechanism 1. Okay, then click OK, and then select this same link, that means our fix, though it's fixed and you can see a fix sign here. Okay, then we want to make the joints. So every joints in assembly or DMU kinematics are made on some references, and that references can be called as constraints. So there is no need to create separately the constraints to join them and separately make the joints. So for separate parts to be get into assembly, you should have create few constraints, and for making some motions or kinematics you should have create some revolutions. But every revolution, every joints in kinematics are based on constraints. So whenever you create a joint, it will automatically create the needed constraints. So we can create the first revolute joint, that's with the fix and the crank. So click on the revolute joint. For every revolute joint we want to coincide two axes and we want to give an offset for the axes. So we want to coincide the first initial portion of the fix and then move it towards the crank. So just roll over your mouse over the sides of the part, so axis will blink. So click so the coinciding axis is okay, so we want to find the offset. So click on this plane and the same side plane of the fix. So all the four required fields are okay, then click OK. Now it came towards this. Then for our convenience we can just hide this fix from here. Click on right click and hide. Okay, then we want to connect the cutting rod. So similarly take the revolute joint from here, then show the axis that means this one, and the second side of the crank. Then show the offsets. Okay, then the 4 required fields are okay, then click OK. Then the third revolute joint, that means the second end of the hunting rod and the initial position of the rocker. Then the offsets are okay, then click OK. Then now we want to connect or make it the fourth and final revolute joint for the 4-bar mechanism, and that's the joint between the fix and the rocker. So we can click on the revolute joint and select this axis and go to the hidden world or swap the visible space. Then you can see the second side of the rocker here, so click there. Then just for your convenience, click on the face, then click on the face here also. Okay, then we can click OK and hide the fix from here, unhide the fix or show the fix from here, so it's in the same position. Now all the 4 links are constrained, that means assemble, and they are also joined with joints. That's all the joints here are revolute joints. For different mode of kinematics, you can create several types of joints, and a collection of joints can be seen here along. When you expand this arrow, you can see several collection of joints. Then in this joint, when you expand the tree from here, applications, then expand the mechanism, then under this you can see the degree of freedom as 1 for the mechanism 1. So the degree of freedom is a rotation in these both direction. So a mechanism can be simulated if when we give an input, all the degrees of freedom of the mechanism is lost. So we have to lose the degree of freedom of the remaining single degree of freedom of the 4-bar mechanism. So just expand the joints in the tree. Then we want to give the input in the crank, angle between the crank and the fix. So click on the revolute joint. Better to double click on it. So joint addition dialog box will be coming. So click on the angle ribbon. So we are going to rotate the angle, the first angle, that's our input angle, that's our crank angle, from a minus 360 degree to a plus 360, that means complete revolution. Then click OK. Now the mechanism can be simulated because the degree of freedom is lost and we have given an input. That means when we give the input, the only single unique degree of freedom is lost, and the mechanism have a self capability or self system to move or work, and it's perfect. That's why the dialog box came. And click OK. So you want to see how these things works. So the motion simulation with commands is here, so click on that. So we want to see what's happening here. So when you scroll this seek bar here, it will work. A kinematics should work on itself, right? So click on the more button, then click on a request, then move this sidebar to here and the initial position, and click this play button. So it's rotating with a high speed, So you want to decrease the speed, then enter the number of steps, that means increase the number of steps. I'm giving it as 200, then play it. Now it got very slow, and you can see them see through many angles. And okay, then you have to analyze what's the change or variation of the angles. So the Catia also give you an analysis platform for the kinematics also, so we can click it from here, analysis. Okay, there is no analysis can be possible because there is no sensors. You can analysis a system only if you are getting